what you're going to learn today in section 13.3 is really, truly fascinating. Fundamental theorem of line integrals. Okay, so let's take this step by step. So, how many recall this fact here from calculus 1 and 2? The fundamental theorem of calculus. It's actually in calculus 1 that you see it, but how many recall that? Sure, you use it a lot, right? Well, there is a, okay, thank you, Eric and Robin. So, you know, there's a fundamental theorem of calculus. Now, you just learned about line integrals in section 13.2. It turns out in section 13.3 that we have a fundamental theorem of line integrals. And that's this theorem right here. The theorem says, suppose you have a smooth curve traced out by a vector function r of t. And the function can be, well, let f be a differentiable function of 2 or 3 variables whose gradient vector is continuous on curve C. Well, it turns out that this line integral, where in place of the vector field you have a gradient field, that's what that gradient of f is right there. It turns out that, well, let me just clarify it very clearly. What this says is that the work that a gradient vector field does in moving a particle from one point to another point in that vector field, in that gradient field, that work can be computed simply by evaluating the function at the beginning and end points and taking the difference. The function starts at the point position r of a, and the particle ends at the position r of b. So there's no like how many remember in section 13.2 when you computed line integrals along some path C, you had to come up with the parameterization for that curve C, for that path C. How many remember that or recall that? Having to find parameterizations of like line segments and, you know, circles and things like that. Okay, Namer recalls it, and Eric recalls it, and you know what this is saying. What this theorem is saying is that all that matters is where the point starts and ends. If the vector field is a gradient field of some function, the parameterization is not needed. Okay, an absolutely fascinating result. Now let's highlight. Maybe I can highlight a few things here. Hold on here. So this theorem, theorem 2, the fundamental theorem of line integrals, says we can evaluate the line integral of a conservative vector field, and actually the gradient of, if the vector field f is the gradient of some function, then that vector field f is a conservative vector field. So we can evaluate the line integral of a conservative vector field simply by knowing the value of the function at the endpoints. Okay, and the line integral is just the net change in the function. Okay, so like for instance, if you had a function of 2 variables and C is a plane curve with an initial point and a terminal point, you would compute the work done, that gradient field does in moving the particle from the initial point to the terminal point simply by this formula. It's that simple. Okay, and you'll notice here in figure 1, they have, well, yeah, I mean, they just show two curves there with beginning and end points. But it doesn't matter the path that the particle takes in going from one point to another point. It doesn't matter. Okay. So let's prove this. Let's prove this. So now hold on here. To prove this, I want to just I want to go to the whiteboard and write something down here. So I don't know why it does that, but okay, hold on. I like things to look good. Okay, so this function here, okay, is, hold on, one moment. Yeah, this function, the function of a position vector, is a function ultimately of what variable? That's right. Good, Ryan. Good, Tom. Good, Christopher. That's right. So if we were to think about writing a flow chart here, well, of course, the let me see here. One moment, class. One moment. I mean, the function is a function of x, y, and z, but x, y, and z are all functions ultimately of t. So if we were to let me see here. Actually, one moment, class. One moment. Let me see here if I actually do. I actually don't think that I need this. I don't think I need this. Let me just hold on one moment, class. One moment. No, I do need this. I do need this. I do need this. Yeah, I do need this. So let me ask you then, if I were to compute, are there any questions on this, what I wrote? All right, if I were to compute d dt, take the derivative of this function of t, by virtue of the flow chart, how many links would there be in the chain rule? How many links would there be in the chain rule? by virtue of this flow chart. 3 sets of 2. That's right, Eric. So, of course, first is going to be partial of f with respect to something. Partial of f with respect, well, let's see here. I'll tell you what. Let me okay, let's put in the rates. First, we're going to have partial of f with respect to what? That's right, Robin. Good. Times what then? What's going to go here? Good. Good. That's right, Robin. dx dt. Okay, and then for the next branch of the chain, the next link in the chain, we're going to have partial of f with respect to so we took care of the first, going down the first branch. Second branch, partial f, good, Ryan, with respect to y times dy dt. Good. Okay. And then finally, we're going to have the partial of f with respect to z times dz dt. Okay, and everything's getting multiplied here, right? Everything's getting multiplied. Okay, and so see, I'm kind of extra careful here because I don't want to put dots there because we're using the dot product a lot now. So I'm going to try to be very precise here. Okay, are there any questions on that? Okay, then let's go back to the book here, and we're gonna prove with this. We can prove this fundamental theorem of line integrals quite nicely. So again, this here. Hold on. That's our fundamental theorem of line integrals, and we're going to prove that right now. So, okay. Here we go. So the integral of the gradient dot dr vector. Well, the gradient of the function is just the gradient of f of r of t, and dr vector is just r prime of t dt. But the dot product then of that function evaluated at position r of t, the dot product of the gradient of the function at r of t with r prime of t is just given by in the second line, the partial of f with respect to x times dx dt plus partial of f with respect to y times dy dt plus partial of f with respect to z times dz dt. But that can be expressed in the third line just as the derivative of f of r of t by the chain rule, which we just showed. Well, on the third line, you have an integral with respect to t of a derivative of a function of t. So the integral and the derivative cancel each other out. They're inverse operations. And so you're left with then the function evaluated at r of b minus the function evaluated you get the function evaluated at the point r of b minus the function evaluated at the point r of a. And that's how you prove the result. Okay, are there any questions on that? Okay, well then let us move forward then. Let us move forward. So there are really important implications here. Really important implications. I want to keep things simple right now. The example one is actually a very nice example, but I want to just keep it extra simple here. Independence of path. Independence of path. Okay, so what are the implications? What are the implications? Hold on, guys. I got too much going on here. One moment. Okay, I mean, what are the implications for this fundamental theorem of line integrals? Well, if you have two curves, two piecewise, they call them piecewise smooth curves, but two curves, and two paths that have the same initial point, beginning point and ending point. So they have the same initial point A and terminal point B. We know from example 4 in section 13.2 that in general, I want to say this the right way, class. The two line integrals of the vector fields along the different paths are not the same. Christopher's saying that's the rule for gravitational potential energy. You mean what's highlighted here? All right, so right, that's exactly right. That's exactly right, Christopher. That's exactly right. If you remember example 4 back in section 13.2, we have that example in the recording, but you had an initial point at -5, -3, and a point at 0, 2, and you had two paths. One is a line segment, the other is a parabola, and we computed the line integrals with respect to both of those paths, and we got different values. But that's not going to happen if you have a conservative vector field. Okay, so one implication of the theorem too is that if you are computing the line integral of the vector field gradient f, okay, and you compute it along two different paths, they will both be the same, because the way you compute that line integral is just by taking the value of the function at the terminal point and subtracting the value of the function at the beginning point, the initial point. So that's called independence of path. That's called independence of path. Okay, that's exactly what that's called. Okay, and how many have heard of that? Somebody chatted that they had heard it. Let me see here. Christopher's seen that. Okay, and indeed it's true, because if you have, I want to make sure I'm saying this very carefully, if you have if the vector field is a continuous vector field, then the line integral is independent of path if the line integrals of the vector fields along any two different paths are the same. And that would be true for a conservative vector field. Okay, a conservative vector field. So like a gravitational field is an example of this, a gravitational field. Okay, and so like for instance, I'll show you an example. I'll show you an example here of this. So like for instance, if I go to the whiteboard, okay, and let's say I have a point A and I have a point B, okay, and let's see, okay, let's say this is my path from point A to point B. And I'm acting in the gravitational field. So my vector field is, let's say, the gravitational field. Okay, I mean, in order, let me ask you this, gravitational field. So to go from point A to point B, and maybe I can, you know, make this a little bit nicer here. Was gravity helping me? Is gravity in the picture here going from the initial point A to the terminal point B? Is gravity helping or hurting that point along that path? Is gravity acting against the path, or okay, it's hurting, right? Going up, you're going against gravity. Going down, you're going with gravity. Okay, but there's a certain amount of work that the gravitational field does on the particle when it moves from point A to point B, and that work is negative work. It's a negative work. Okay. All right. Well, let's take another example here. Let me have, you know, here's point A. And here's point B. Okay. Here's point A and here's point B. Okay, and what I'm going to do here is I'm going to go along this path. Got to be a little careful here. Hold on here. One moment here, class. For some reason, I'm not able to get this to go. All right, let's go. Okay, I'm going to come back to this. Let me stop the recording. Let me stop the recording. Let me stop the recording.